Before we get started on translation, the second part of building a protein, I want you guys to practice and go through this check your understanding. So pause the video and get started. If you didn't already, be sure to check your answers from the Check Your Understanding checkpoint and then continue with our video. So in this video, we're going to be talking about translation, which is the second part of protein synthesis. So first, we had transcription, and that was occurring in the nucleus. So in transcription, we were going from DNA to our message. And why do we need a message? Because DNA can't leave the nucleus, and only the mRNA or the message can. So it's kind of like right now, some people in San Francisco that can't leave their house. What they can do is send a message through Amazon, say, hey, send me a package. So they're not physically leaving their nucleus, leaving their house, but they are sending a message to a delivery service who can bring them what they need. And that's kind of like our mRNA. DNA can't leave, but mRNA can go and send a message. And our mRNA is going to go to the ribosome, and that in the cytoplasm in the ribosome is where translation is going to be taking place. So translation is going to convert our message into that polypeptide or protein. Polypeptide is just another word for protein. It's a chain of amino acids. They are synonymous. Amino acids are coded by the mRNA bases, which again, our mRNA was just the message of our DNA. Translation is going to convert the mRNA into a polypeptide or protein. And this is occurring in the ribosome. So in the nucleus, we went from DNA to mRNA, and that was the process of transcription. And now outside the nucleus in the cytoplasm, in the ribosome, that is where that message or mRNA is going to be converted into a protein. So what does that look like? So just like some languages aren't all read the same way, our mRNA language is read by the ribosome in groups of 3 nitrogen bases at a time. And these are called the codons. So the ribosome is going to read through 3 letters at a time. And one of these codons codes for 1 amino acid. So a codon codes for 1 amino acid. As you can see here, the codon AUG, again, 3 letters at a time, gives us 1 amino acid. And then if we keep reading on our message, the next codon is GUC. That's going to give us another amino acid. And we have another codon, AGU, and that gives us 1 amino acid. So each codon only codes for 1 amino acid, and a codon is always going to be a sequence of 3 RNA nucleotides on the mRNA strand. So 3 mRNA nucleotides is 1 codon. And 1 codon gives us 1 amino acid. The first codon in our mRNA is always going to be the start codon. That will never change in our message sequence. So mRNA begins with start codon, and that is AUG. So our start codon on our mRNA is always AUG. And our ribosome and our tRNAs, which are going to be transferring or carrying these packages, these amino acids, they know when they read the mRNA, they know what amino acid that codes for. We don't. So scientists came together and made a simple little chart for us to be able to know what each codon codes for, what amino acid it codes for. And that is the codon chart. So let's say we have the start codon, A, U, G. So that's our start codon. What amino acid does that give us? So you start here with the first nucleotide, A. And then the second nucleotide is U. So I start up here, the second nucleotide, U. So I'm going to go down to this column and this row, A, U, and my last letter is G. So I'm going to look for the last letter, or again over here, last letter, third codon is G. So my first amino acid is MET. So that codes for the amino acid methionine, or MET. If my mRNA strand is A, U, G, U, U, C, G, G, A. So let's see, our first codon, remember, groups of 3 nucleotides. So the second codon is going to be U, U, C. What would that give us? What amino acid does U, U, C give us? And that is the amino acid phenylalanine, PHE. The next codon would be GGA. So I look G and then go over to second codon is another G, A, and that's glycine. So G, G, A would give gly. And this is how the ribosome is going to go through and read one codon at a time and bring our tRNA will bring one amino acid at a time to the ribosome. So we can start to build the protein. And again, it's based on the directions of our message. So other items needed. Besides the message, we need the ribosome, which we're going to draw out in our diagram. We also need our transfer RNA. So our transfer RNA is kind of like the delivery truck. So think of it as if you place an order on Amazon, you're not physically going to the Amazon store, but you're telling through a message what you want. And then they have delivery trucks that bring it to you. But how do they know where you live? How do they know where to bring it? And that's because you put your address in. And that's kind of like our tRNA. They have the address or the anticodon. So the anticodon is on our tRNA, and it's like the opposite of our mRNA codon. So they know exactly where to bring that amino acid. And that's all they do. They just carry the amino acids from the cytoplasm to the ribosome in the correct order based on our mRNA. And it knows exactly where to bring it because it has the address or the anticodon. Let's draw this out. So a few things to label first. So this is representing our nucleus. Remember, DNA cannot leave the nucleus. And these are our DNA strands. And this is going to be our ribosome in the cytoplasm. So remember, in transcription, the mRNA is edited So remember, our mature mRNA is just the exons. It was edited, the introns were cut out, so now it only codes for a protein. The mRNA is going to leave the nucleus and go to the ribosome. It's going to form the complex. And the other thing I want to draw is our tRNAs. Those are going to be in the cytoplasm, and they are free-floating in the cytoplasm until they are needed. And again, RNA is single-stranded, so our tRNAs are single-stranded. And those are just free-floating in the cytoplasm. And they transfer, they carry amino acids, but they have to know where to deliver them. And so they have the address called the anticodon. So in your tRNAs, we're going to label, we have the anticodon, that's going to be the opposite of the codon. Like the delivery address where it has to know how to bring them, and they also carry specific amino acids. And each tRNA carries a different amino acid. The function of our tRNA is to carry the amino acid from the cytoplasm to the ribosome. And again, we're in the cytoplasm of the cell. So they're going to transfer the amino acids to the ribosome according to mRNA directions. Remember, the mRNA got its message or instructions from DNA. So it's going to carry them to the ribosome, and we'll see what that looks like. And each one has a different amino acid, so we'll draw another one there. So in the ribosome, in order to form this complex of both subunits together, the mRNA is going to attach to our small ribosomal subunit. So we'll draw our RNA, will transfer the amino acid and the correct amino acid according to the mRNA to the ribosome. So here at the ribosome, we have our messenger RNA that we're going to put in to the ribosome. And the messenger RNA holds the message of which protein to build based on our DNA. So we'll fill in the nucleotides A, C, A, U, G, G, A, C, A, U, U, A, G, U, A. So this is our mRNA strand. And our ribosome is going to read our mRNA strand one codon at a time. Remember, a codon is a group of 3 nucleotides on our mRNA strand. Our ribosome actually has 3 little loading dock sections, you can think of them as our A site, P site, and E site. So let's draw those in to our picture. And the ribosome is going to have these 3 little loading sites where tRNA will come, drop off the amino acid, and then they are released once the amino acids have been linked together. So here are our 3 sites. So our picture We can't move it, but our ribosome is going to ticker across reading one codon at a time, and then it's going to keep going until it reads the entire mRNA strand and comes to a stop. And there are 3 possible stop codons. So our first codon is AAC, but remember, our starting point, our start codon, is always AUG. That's our only start codon. So the ribosome won't start until it reads AUG, and that is our start codon. So this one doesn't get read. So our start codon is AUG. So let's see what amino acid AUG codes for. AUG codes for MET, and that's always going to be our start codon. So we're going to fill in a tRNA that is coming in, and it's carrying the amino acid MET, our start amino acid, MET, or methionine. And so that tRNA comes in, but how did it know to come here and not any other section of our message? And that's because of the anticodon, or the delivery address. So the anticodon, it's still RNA. So if this is an A, on our tRNA will be U. If this is U on our tRNA, the anticodon, or antinucleotide will be A. And if it's a G, the nucleotide will be C. So this is our anticodon. It's how it knew where to go, where to bring methionine. Our next codon that the ribosome will read is GAA. So let's look. GAA is glue. So that is our next amino acid. So the tRNA coming in is going to be carrying the amino acid, and I'll pick a different color for this amino acid, glue. And the ribosome, what the ribosome is going to do now is it's going to form a bond between these 2 amino acids to start linking them together to form the protein. And that bond is called a peptide bond. So our amino acid will form the peptide bond. So we got moved around here. I will form the peptide bond. The ribosome is going to form a bond to connect these 2 amino acids, and that is called the peptide bond. The ribosome will form a peptide bond. Once these are linked, then this first tRNA carrying our methionine, it can leave and go back to the cytoplasm and find more methionine amino acids. So first tRNA will leave and go back to the cytoplasm. To find more or another amino acid. Remember, tRNAs are specific. They can only carry 1 amino acid. So that one will find more methionine, but this is going to keep happening. So we'll erase our tRNA, and you don't have to do it on yours. You can keep him, but the tRNA will leave. And then this tRNA that was in our second spot is now going to shift over, making room for the next amino acid. That's going to be coming in on the other tRNA. And our ribosome is also going to be tickering or shifting along, reading our message strand. So the next codon is CAU. Let's see what that code's for. CAU. So CAU, histidine. So we're going to draw our next tRNA, carrying the amino acid hist. How did it know to go here and not somewhere else? And that is the anticodon. So the anticodon for our amino acid, so our amino acid is histidine. So the anticodon for our tRNA, so anticodon for our tRNA that is carrying histidine is going to be G, and then A goes with U, and U goes with A. This is just the delivery address. It's just so where it knows how to go. And then again, our ribosome is going to link the amino acids together. Now this tRNA is going to leave, because remember it shifted over, so now it's going to leave. And then now this tRNA is going to shift over. And you'll see this better in the Amoeba Sisters video you're going to watch for homework. Our ribosome is going to continue reading this entire mRNA strand, linking amino acids together and building until it comes to a stop codon. Once it comes to the stop codon, and there are 3 stop codons, you can see 1, 2, 3. We have 3 stops, 1 start. Once the ribosome comes to a stop codon, then our mRNA strand is released, and this polypeptide, or the protein that was built, is going to go to the rough endoplasmic reticulum to be folded into its proper function.